Okay, hi. Welcome to the fifth Math Teacher's Code. I am Yoni Nazarathi from One on Epsilon, and we'll be dealing today with equation solving, and if we have time, with some optimization. Just to recap, you can go to our YouTube channel and look at the playlist Math Teacher's Code. There have been 4 previous sessions to this one. Following these sessions is not necessary for following today's lesson, with the exception of perhaps session number 1. So if you head on to session number 1, then you'll see the basics of setting up Julia Box and getting Julia running. And I'll also be following comments, so if anybody has any questions as we go, then just key in your comment and hopefully I will notice it and can interact. Okay, so what are we going to do today? Let me go here to Epsilon stream and I'll key the quadratic formula. We all know the quadratic formula, we being mathematics teachers, secondary, high school mathematics teachers, and our students study this, and it's all about finding the roots of the parabola, where it crosses the x-axis, right? The thing is, how often do we try to do to find a solution for such a thing numerically, say without using the formula itself? Now in the case of a quadratic equation, there's no need. Of course, you have this incredible result, you know the solution of the quadratic equation, but the fact is that in practice, many equations are actually solved numerically. So this is a type of thing that we will explore today. So I've gone on to Julia Box and I'm logging into Julia Box using the Math Teacher's Code account. And if you haven't tried logging into Julia Box, just make a new account with them. You can either authenticate via Google or use any other email address if you'd like and start computing for free. There's also paid versions of Julia Box. That's if you want dedicated servers for you. But I'm using here the free version and I've launched. And at this point, what Julia Computing is doing is setting up a host with Math Teacher's Code. So these are all of the sessions that we've had previously in Math Teacher's Code. By the way, you have links to, and you can get these files in the comments under each of the videos. Math Teacher's Code. Okay, so we're in Julia Box and we're going to do a new Julia 1.0 and create a new notebook. And what are we going to do? Well, first of all, let me just change this cell to a markdown cell just to write something. So instead of code, I'm selecting markdown. I can also do that by just hitting M on the keyboard, and that converted the cell to markdown. And I'm going to write the equation, the quadratic expression. So let me actually design an expression that I know that has some nice roots, some integer roots. So let's say x minus 4 multiplied by x plus 2. So that's actually x squared minus 2x, right? So minus 4x plus 2x is minus 2x minus 8. Okay, if I expand the, if I open up the factors. And when so by the way, these dollars, that means that I'm just writing a formula in LaTeX. This is not necessary for making code in Julia, not at all, but it's a way for me to express things nicely. And you see then if I hit Shift Enter on the cell, it is formatted and we have this expression. So we're going to look at this quadratic expression. Okay. Now this expression has roots at 4 and negative 2, well, by design, right? Let's see that. Okay, and to understand that this has roots at negative 2 and 4, well, of course, just to recap what you know and what your students probably know at some point, is that if we're looking for asking for what values of x does the following hold, right? And if you write this quadratic expression in the way that we designed it, x minus 4 times x plus 2, we see that to get the right-hand side of 0, we need to choose either x to be 4 or x to be negative 2. Okay, so that's all nice and good. And at this point, let's first of all just create this expression programmatically. Let's create some plots. Let's visualize what these roots mean. And then later on, let's actually move and try to find them in a way that does not rely on incredible mathematics developed in the last, well, 1,500 years really, or 1,000 years of algebra. I'm actually not sure in what year exactly the quadratic formula was put forward. Probably around 500 years ago or so. So for this, let me define a function in Julia, and I'll just call this function f. Because I'll have other functions later on, I'll call it f1. So f1 of x is going to be a general quadratic function. That's a times x squared plus bx, b times x, plus c. Okay, so if I evaluate this cell, shift enter on this cell, the function f1 of x is a generic function with one method. Okay, so it's an alternative way to write this, just reminding you in Julia, so I could have done function f1 of x and then have written a return value of this. Or alternatively, I could have not had this return value, and the last expression in the function is the return value. So this is what the function evaluates. In this case, the Julia language function is nothing but the mathematical function, which is a quadratic function, a polynomial of order 2 evaluated at the point x with some parameters a, b, and c. And let's also indicate what a, b, and c are. So I'm going to do this as follows. I'm going to say that a is 1, and b is negative 2, and c is negative 8, in agreement with the expression that we wrote above. So in line, I'm doing escape L so we see line numbers. So in line number 1, what we actually have is we're assigning to the variables a, b, and c the respective values 1, negative 2, and negative 8. This is effectively what's called a tuple, what I've just highlighted in Julia, and it's assigning elements of the tuple to these variables. Okay, so this makes this function concrete. Let's plot this parabola. Okay, so using pyplot. Okay, and then we will create a range of values. So let's go for a range of values, x range, to be between negative 3 in steps of 100th up to 5. Okay, so this is what we call our x range. And the plot function of the pyplot package is actually a very simple function. It's just a function that requires here x values, comma, y values, and the number of x values needs to agree with the number of y values, and it plots those corresponding dots in the Cartesian plane and connects them with the line. That's the only way that the plot function works, or that's the way the plot function works. So if we plot the x range, what we want to apply, you know what, it won't hurt to actually call this the x domain. So let's call this the x domain, okay, so we don't confuse the mathematical meaning of range and domain of the function. So the x domain, let's plot this parabola on the x domain between negative 3 and 5 in steps of 100th, okay? And then let's evaluate the function on x domain. Okay, these are going to be the y values. However, the function evaluated on the x domain, this function expects a scalar, expects a single variable x. If we do f1 dot x domain, dot, and we've seen this in previous sessions too, that's the broadcast operator in Julia, that effectively maps the function f1 on each and every value in x domain. Okay, so that's that. So if I run this, in the first run when I'm running this cell, Julia is taking a bit of time, and that's because I've just just put in line number 1 using pyplot, and Julia is actually compiling the pyplot package for the first time. Notice that if I run the cell again, it's much quicker. Well, relatively quick, but quicker. And well, in the third time it'll be even quicker. There's also compiler optimizations that are happening between each run. So what we see here is a plot of the parabola. Okay, and let's plot this parabola in red. So I'll put another argument to plot, and that'll be in quotes R, and that says that the parabola should be plotted in red. And let's also, in a very brute force manner, just plot the x-axis. So for this, I'll choose something like the vector -3, 5, comma 0, 0. So this just specifies 2 points in the Cartesian plane, the point -3, comma 0 and the point 5, comma 0, and it will connect them with a line. Let's make that line blue. Okay. And here's our plot. Now we expect the roots of this parabola to be at -2 and 4 as the plot shows us. So no surprise here. One can even say, hey, I could have done this in about 5 seconds in Desmos. Why do all this code in Julia? Well, we're going to do some things that are a bit more fundamental than just using a graphics calculator, as good as it is. Okay, so the first step, let's actually put dots on the solution so we just see what the solutions are. And for this, let's still not solve for these solutions in any systematic numerical manner, but let's just create a function sols ABC, and let's tell ourselves that this function, I'll put a comment above, this returns the tuple of solutions of the quadratic equation ax squared plus bx plus c equals 0. Okay. So when I mean tuple, I can put here, like, for example, 2 values. I could have put 4, comma, -2, and that's a tuple. Okay, that's the tuple is a pair of values or a sequence of one or more values, and it's a slightly different data structure in Julia in comparison to an array. Okay, so that's a tuple. So let's create this return value, and I'll simply use the quadratic formula. So I'll say -b plus or minus, so let's choose minus, square root of b squared minus 4a, 4 times a times c, all divided by 2a. Now you can actually put the constant 2 here next to the a, and that means 2 times a. Okay, so that's going to be the first value, and the second value is going to be the positive of this. So here we're using the quadratic formula. Okay, plus. Okay, all right, let's now say solutions, which would be the tuple, the variable of solutions, is going to be the function sols applied on R, A, B, and C. Now notice something. These A, B, and C, I could have called them something else. I could have called them my A, my B, my C, and then use these variables here. These are the local variables within the function defined and implemented on line 7. Whereas here, sols ABC uses the global variables ABC. That's slightly different to what's happening in line 4, where here the function in line 4 is actually using the global variables ABC defined on line 3. But these are programming subtleties that you can actually skip on a first go if you didn't fully understand what I said at this point. So let's even do a print len, which is a print. The roots of the equation are, and then let's put the solutions. Okay, let's run this. And now we had this kind of unpleasant effect where the print len of roots of equation, we had the start of the printing here and then the plot and then the end of the printing. Let me just throw the printing to appear after the plot. And sometimes there's no full control on what's exactly happening, on what the Jupyter notebook returns first as output, the graphics output of the figure, or the output printed to stdout. But that doesn't matter much. So what you see is that we have the roots of the equation -2, 4, 0. And of course, if we would change here the values a, b, and c, then the values passed in line 8 to the function sols would be different and would get different roots. Okay, this is still using the good old classic technology, the beautiful result of the quadratic formula, which you can teach your students without any use of computers at all, of course by completing the square and proving it, but that's not our business today. What we do want to do is to actually put these two solutions on the graph. So let's now plot the solutions. So I just want to put two green points. So for this green, I'm going to do a G dot, and that's going to be a G point, and I'm going to put the coordinates of the solution. So the first coordinate is going to be solutions 1. The second coordinate is going to be solutions 2. That's how I'm accessing the elements of the tuple, and I'm going to put this at 0, 0. So if I run this, there are actually two green dots there, but they're a bit small, so I'll use another option for pipe plot, which is ms, and let's try 20, and that's the point size. Okay. So what at least we got at this point is a visualization of the parabola that we're speaking about, the x-axis, the points where the parabola intersects the x-axis, and of course we see visually that these points, -2 and 4, are these points, and we got that via the quadratic formula. Good, that's great. Well, let's now try and find these points in a completely different manner, in a manner that's actually much less sophisticated in many ways than the quadratic formula, which is a feat of algebra of the past 1,000 years. Let's actually just search for every little point on X domain. Okay, so X domain is a finite grid. The computer here approximates a real line with this finite grid, the X domain. And let's see where the parabola changes sign and crosses the x-axis. That is, in a sense, the most brute force method of numerically finding roots of an equation. Of course, there are many other methods, much more sophisticated, bisection, Newton-Raphson, and a variety of other methods. We're actually not going to do these today. We're going to do the basic brute force method. But by programming the brute force method, first of all, we'll learn a bit more programming, get a bit more experience with programming. And I do believe that this is something that you can do with your students. So if your students are actually dealing with a quadratic formula, quadratic expression, solving quadratic equations for months and months and months, and sometimes more, well, maybe for a week or two, they can actually program it and see that in a brute force algorithm they get that. And later on we'll motivate this more by actually changing from the parabola to a much less trivial equation. Okay, so one thing we can do is we can use a sine function, question mark sine. So let's see what sine is all about. Well, sine is x. It returns 0 if x equals 0, and otherwise it returns, and this is kind of a smart way of saying it, returns x divided by the absolute value of x. So if x is non-zero, right? You cannot divide by the absolute value of x if x is 0. So it either returns +1 or -1 if the sign is positive or negative, or specifically if x is 0, it returns a 0. So we can apply sine to the function sine to our function f1 applied to the x domain. Let's try that. Okay. Just before I do this, look first. I have f1 applied to x domain. We get an array with 800 elements, which are exactly these values of the parabola. We just see Julia is just printing the first values of this array, the first few values, and the last values, and there's a whole bunch in the middle. Why 800 elements? Where 800 are the number of steps. This is kind of -3 to 5. 800, 801 in this case. Okay. Now, if we apply the sine function on that, and again, I'm using dot because I'm broadcasting the sine function to each element of this array, then what we get is an array of, well, we just see here the ones, but hopefully there are also some negative ones in the way, right? We probably just see the ones because the sign is positive for x at the start of the array, and it's positive for x at the end of the array. Okay, so let's call this new array of signs, let's call this SGN. Let's plot it. So let's just plot X domain versus SGN with R. And with a red color, let's also plot an axis just so it's clear. So between -3 and 5, 0, 0, let's make that blue. And then I got a syntax error, sign after expression, so if I do sign equals. Now, it might be that you're seeing me and I'm coding rather quickly and not getting so many syntax errors. Well, first of all, I did have a dry run of this before. And second of all, I do work quite a bit with Julia. So don't be hard on yourself if you're actually working and getting a whole bunch of syntax errors. Often a way to debug, to find, to at least, well, to see where you're getting errors of this sort is to comment things out as you code and then narrow down where to see where the problem is. Okay. So what we see here is the degenerate parabola. Well, very degenerate. The plot, the out of 15, shares the same sign as the plot of out of 10, but has clearly lost the magnitude because the values are just at 1 or -1, but it retains the same behavior of being either positive or negative when the parabola is positive or negative. So how about that we actually now run over each value in X domain and see when the sign is positive and when it is negative. And whenever there's a sign change, we'll say, haha, there is a root. Now this is no longer specific to the parabola. We can do this for any continuous function over a domain. Right, so a continuous function over a domain, that means that effectively if you're drawing the function, you do not lift the pen from the plot or from the paper, and that means that if you change sign at one point, then there is a point in between, well, based on the intermediate value theorem, but there is a point in between that crosses the x-axis. So that would be our way of finding the roots. So what we can do is we can loop over all of the elements in sign. Okay, so we've got this array sign, right? It has 801 elements. So we can loop over all the elements in sign. So let's first of all set I as some index and let's let it run from 1 to the length of sign, SGN. I should say SGN, not sign. Okay, length of SGN. It's going to be 801. So we'll loop over all these elements. And each time we're going to say if, and what we're going to say if sign change. Okay, we'll implement the condition for that if in a second. Okay, if sign change, then we'll say println sign change at comma I. Okay, not I like that, but I like that. Okay, so this is going to loop over every index of the SGN array, and every time it's going to check if there's a sign change. Now, how do we check if there's a sign change? Well, the condition for sign change means that the sign at the index I does not equal sign at the index I plus 1. That's what we mean by sign change. Okay. So as we iterate here for 801 iterations, line number 2 is going to be evaluated again and again and again and again. And each time the line will check, hey, is the sign at the index I equal to the sign of the index I plus 1? Now, does anybody see a problem here? So what is the last value of I that this loop, lines 1 through 5, is going to get? It's going to get the length of SGN, which is 801. And then in that 801st iteration, I plus 1 is going to be 802. And we're going to try and attempt to do something like this. So let me show you. Let's make a cell below. Let's do SGN at 801. That still works. But SGN at 802, oh, Julia is not happy anymore. Bounds error, attempt to access 801 element at index 802. So we have an 801 element array and we're trying to access it at index 802. Okay. By the way, if anybody's wondering, in the classic language C, You can access arrays out of bounds as much as you want, and C won't get mad, but you'll actually get some horrible other types of bugs. Okay, but Julia, like most modern languages, actually checks for array out of bounds indexing, so you cannot access sign at array 802. And indeed, if I would run this here, then I got some output, which we'll investigate in a second. But then we had a runtime error, which is, hey, we've accessed this at array 802. So how do we fix this? Well, if we're comparing the sign over 801 elements, each time between one element and the next, then we should let I not go from 1 to length of sign, but rather to the length of sign minus 1. Okay. And here, since I'll keep this in the output that I put, I'll put here an example of a runtime error. Okay, a runtime error is different than a compile time error. The error that we got before, for example, for doing this, for doing SGN and then square root of 244, this is a compile time error. This is a syntax error. Okay, so you can get different types of errors. You can get runtime errors, you can get compile time errors, or you can get logical errors. Okay, so this is an example of a compile time error. Now, Julia is actually a compiled language. That's what makes it cool. It's different than Python or JavaScript, which are interpreted, and that means that the environment that's running the language is checking for the syntax for what you're doing line after line. And Julia, actually, every time we run one of these cells, it's sent to the kernel, and the kernel compiles it and creates machine code that then runs. And that's what allows it to be fast. Okay, back to our business. So what we're doing here is we've got this loop in line 1 through 5, and we found some sign changes. So there's a sign change at 100 and a sign change at 101. That's a bit odd. So at the index 100 and the index 101. And then there's a sign change at 700 and a sign change at 701. Okay. So what's happening here? So first of all, let's look. These i's, they're not values of the x domain. So we've got the x domain, right? They're not values of the x domain. They're indices into the x domain. So let's look what's x domain at 100. X domain of 100 is negative 2.01. That looks quite promising. We know that this parabola has a root at negative 2. And x domain at 101 is negative 2. But I kind of don't like this, because there was an indication that there is a root, a sign change is a root, right, for a continuous function. There is an indication of a root both at negative 2.01 and at negative 2. The 0.01 stems from the discretization that we imposed. That's here in line 9 of this first block, and that's the steps of 1/100. We could have gone with much finer steps as well, and hence gone much larger arrays. Okay, so this looks kind of promising, but it's still not the exact thing that we want. How about x domain at 700? That's indeed 3.99. And x domain at 701 is 4. Okay. Now, what's happening here is that the sign function, if you remember the documentation for the sign function, it actually returns an exact 0 value if the function equals, if its input argument equals 0 at that point. So effectively, there was a sign change. So if you look, let's look at x domain from 99 till 102. Okay, that's not what I wanted, but let's look at x domain 99, x domain 100, x domain 101, and X domain 102, X domain 102. On those four values between negative 2.02 to negative 2.01, negative 2.0, and negative 1.99, there was probably a value where the function f was exactly 0. It was positive 1 and it was negative 1. So how do we do this? Let's look at, not at x domain, but let's actually look at sine SGN at 99, SGN at 100, SGN at 101, and SGN of 102. So as you see, there was between 100 and 101 there was a sign change, as we were informed, sign change at 100. And between 101 and 102 there was another sign change. But this sign change is not an interesting sign change for us, right? Only one of these two sign changes is interesting. So we've doubled up on sign changes. There are not 4 roots to the parabola in this case, but only 2 roots. I want to say in this case there can be also 1 root or 0 roots, obviously. So let's now, after we have this insight, so what we see here is a bit of runtime debugging. The program works, but it's not actually giving us exactly what we want. So let's modify it slightly. And there are different ways to do this. What we can do is we can say, let's only flag a sign change if the sign of I is not the sign of I at I plus 1, and also the sign of I does not equal 0. Okay. So let's rule out this logical AND cases where the sign of I was 0. And if we run this, then we've got exactly a sign change at 100 and a sign change of at 700. Okay, so we've got now the 2 indices of the X domain where there was a sign change. And that looks quite healthy. Let's now do one more thing. Let's create the roots array, which is going to be an array of solutions to the equation. Okay, and whenever that happens, instead of actually printing out, so I'll actually duplicate this line. So let's let this run and be here. Instead of printing out, hey, there was a sign change, let's record them in the roots array. So in line number 1 there is an empty roots array, and now in line number 4 what I'm going to do is enter this new root that we found to the root array. So what is this new root? We will push into the roots array the X domain at I. Okay. And let's return as an expression from this cell the roots. Okay, so this code snippet is the first code snippet that we've actually seen that really gave us an approximation for the roots. Okay. Now you can see that this approximation is perhaps a bit crude because it's not exactly, the roots are negative 2 and 4, and we got negative 2.01 and 3.99. But that has to do with the fact that we've chosen a grid which is only good enough up to a resolution of steps of 1/100th. Yeah, 10 to the minus 2. This is certainly a good enough grid for plotting nicely. But for finding the roots, in this brute force manner, it only gives an approximation. Okay. Now we could have improved on that a bit. We could have, for example, said, if that is the case, and we're not going to push these roots, then we will push, let me create a slight improvement in this next cell. Then we would say, let's take X domain at I plus X domain at I plus 1 and take their average. Okay. So what this says is, well, if we had a crossing of the x-axis at the index I of the array SGN, then let's interpolate between the value before the crossing and the value after the crossing. The thing is that this is not exactly the value after the crossing, again, because we were quote, lucky enough to have the function cross at the index I exactly at 0. But this block of code does a slightly better job. Okay, having done all that, let's now actually create a general function, and we'll call this function find roots. It's our function for finding roots. And what this function will do is we're gonna give it as input a mathematical function, which is also going to be a Julia function, and it's going to numerically find all those roots within a given interval. Okay, so the functions that we've had up to now, the Julia functions that we've had up to now, such as f1 and sols, and also functions in previous editions of Math Teacher's Code, all got as arguments things that we expected to be vectors or mostly scalars, variables. Now this finds roots function, it's actually, we want to give it f, which we assume to be a function, and some grid. Okay, so let me actually say what this function does. I'll document it, put a comment above the function. This function looks for roots of the mathematical function f over grid. Okay, so you would use this function, the way we would use this function, we'd say find roots. We still need to implement it here, right? Still need to implement it in lines 3, 4, etc. But once it's implemented, we will say find roots, and we'll give it, for example, our function f1. Our f1 is our parabola, and we'll say here's like a grid between -10 and steps of 0.01 to 10. Okay, so say we know nothing about the parabola, and we're saying look for any roots that you find in this grid. Okay, this is how we would use this function. So how do we implement this function? Let's copy this code here. So it's often the case that when we make functions, at least in this Julia environment, and in Jupyter in general, you can play with code in cells, and once you kind of like what you have, you would package it inside a function. And now let me format it with some nice indenting. Okay, and we like to have things indented so that it's visible that all of the lines 3 through 9 are the internal working of this function. So line 9 has roots, that's equivalent to writing return roots. So let's now look at our function, and still not exactly, it's not just right. Okay, so the function find roots gets a mathematical function f in a grid. Now the thing is, the codes in line 3 to 9 don't use f nor grid. They use something like SGN, and they use X domain. So first of all, we need to say what SGN is for this function. SGN is going to be the sine function applied to the function f applied to grid. Now line 3 is quite a complicated line in the sense that it uses the function argument f, which was given to find roots. Right? So find roots is a function, it is a procedure that gets a function f, and whatever that function f is, Julia will apply it using the broadcast operator to anything in grid. It assumes that f is a function that can be applied to grid, and grid is a grid of values over the x-axis, and that's going to be the SGN. So that defines here SGN. Now here in line 7, what's a problem? We're using the name X domain, but this function does not know X domain, it knows grid. So let's use grid here. Okay. And this might work. Well, let's try this. That's pretty nice. So when we gave it the function f1, and we said find all the roots between -10 and 10 with this discretization, we actually got these values, and notice that they're more accurate than what we had before because we gave the function a finer grid. Let's play around with our new toy a bit more. Let's just see that it's kind of sensible. So if we give even a finer grid, now this fine grid we have to think for a second. So we got here 1, 2, 3, 4, 5. So that's 10 to the 5 and another 20 steps. So this is a grid of about 1 million values. So that means that when the function findRoots runs, in line 3 it's going to create the SGN array with about 1 million values. And then it's going to do 1 million iterations, which is not a big deal for Julia. But still, keep in mind that that's the case. And then we get a much better explanation of the roots. Let's just see that this function really is general. It doesn't, we have our new toy, this function. It does not care that f1 was a specific parabola. For example, let's make f linear f. That's going to be our linear f. Is going to be 2x plus 3. Okay, it's a linear function. Okay, let's find roots of this linear f. And it says that the root is at negative 1.5. Let's think about it. Negative 1.5 times 2 plus 3 is exactly 0. Wow, it worked. So you can give this now any function that you'd want, and you would find the roots. Okay, that's this function, find roots. Okay, now to motivate this in a teaching environment, so this is one thing that I would do. I would consider a situation where students have already had some practice with the quadratic formula, with quadratic expressions, with algebra, with understanding what roots are, etc. And then I would go for a function that's actually more obscure and is not solvable analytically. I mean, this parabola is solvable analytically. You can actually find its roots as clearly this linear function that we had here. Okay, but I would go for a slightly different function. So how about this, for example? Let's look at the function f2 of x, and it's going to be the same function we had f1 of x, but plus some oscillatory term. So something like 2 times the cosine of 20x. Okay. Let's look at this function. Plot x domain of f2 applied to x domain with red, and let's also plot a axis -3 to 5, 0, 0, blue. Now I'm going to put a semicolon after the plot command here, and that semicolon suppresses textual output of the plot. Textual output such as, for example, this stuff. Right, so this was textual output of the plot that wasn't really meaningful for us, and that's because we did not put a semicolon here. So here I've put the semicolon. Now you see this is kind of a wobbly parabola, the wobbly parabola. We all know how to solve quadratic equations and find roots of non-wobbly parabolas, but this quote wobbly parabola, well, it's a parabola with a cosine term on it that kind of makes it wobble a bit. As you can see, there are multiple roots for this parabola. So finding the roots of such a parabola analytically is actually a complicated task, a challenge for anybody. And please, if you find roots for this analytically, please share in the comments to the video how you did find roots for this parabola analytically. But let's now just find the roots using our new machine, find roots. So find roots of f2 on the grid, say -10 in steps of, let's say, 1000s up to 10. You see this parabola has roots at this wobbly parabola. It's not a parabola at all. Claims to have roots at somewhere around -2, and I do actually see how many crossings here: 1, 2, 3, and -2. And it claims to have 4 positive crossings at around 4. Let's see if there's really 4. 1, 2, 3, 1, 2, 3, 4. Is it 4 or 5? There's 5. 5 crossings around 4. Okay, so there's a total of 8 roots to this equation. Now, in practice, and this is something that many secondary school students don't really internalize, and as teachers, it's our job to kind of tell them that that's the case. In practice, most of the equations solved in weather prediction, in engineering, in actuarial studies, that's in insurance, and in many, many other applications, equations do not have analytic solutions like this beautiful parabola. I'm not saying that most equations are as wacko as this, but often they're equations that live in high-dimensional spaces, and clean, simple analytical solutions are not available. So actually understanding the concept of root finding in a completely numeric manner, as brute force as this numeric manner is important. It's important for students because this is how mathematics is also used. Okay, let's plot those roots just so we feel good about ourselves. So what I'm going to do now is just create a plot of the positive roots that we found, and I'll do it pretty much as follows. So I'll call something like find domain is going to be 3.5 in steps of 0.01 to 4.5. So I just want to plot, I just want to zoom in between 3.5 and 4.5, and I need to do this programmatically. And then I'll create a plot of find domain F2 applied to find domain, create a red plot, and also plot the axis for this, and I'll plot the axis between 3.5 and 4.5, 0, 0, create a blue axis again, and then we want to actually plot these points. Now, to make it a bit interesting, let's look at our roots. There's this array called roots, right? This is array of point roots. So we only want to take the positive roots. So for this, let's use a built-in Julia function called filter. Okay, and as filter sounds, that's what it's going to do. It's going to get a function as an argument, and it's going to get an array, and it's going to filter from the array all values for which function evaluates to true. Does this look familiar? So filter gets a function as an argument. Our function find roots also got a function as an argument. And that function doesn't have to be written as f. It can be a g or it can be any other expression. F is just a simple way to do that. So if we will filter roots with the function, and what I want here is a function that returns true if positive, okay? And then we'll give it roots. So that's what I want to get as the first argument for filter. We will filter only the positive roots. Okay, well, how do we do this? Well, one way to do this is to create a function here, and we'll just write it in one line, is positive on a variable x, and it returns if if x is greater than 0. Okay, and then I could write here is positive. So let's see what happens here. So you see the filter function only filtered out only the positive roots. We only got the 5 positive roots. But there's actually another way to do this, because this, which is syntactically nicer. So here in line number 1 we had to kind of define a function and then use a function in line number 2, but we might never use that function again. So instead what we can do is we can actually define the function as an anonymous function, and we'll write filter, and we will say x arrow x greater than 0 roots. Now this text that I'm highlighting here is kind of a strong bit of text. To be a bit clearer, let me put it like that. And it is a function that is defined anonymously and only lives for the duration of line number 3. And it effectively acts like this is positive function. Okay. So this is a this is a 2-line implementation, line 1 and 2, and line 4 is going to do the exact same thing. By the way, we could have done the same thing with our roots function. So you want to see that, so I'll digress for a second. So our find roots function, we're happy about our new tool, right, to find roots. So what if we wanted to find the roots of the function, say absolute value of x minus 1? Okay, for those of you that can visualize it, the absolute value of x is this function that goes, and I'll show with my hands, exactly like this, touching the x-axis only at 0. But if we subtract 1, then it should have two roots, right, at -1 and +1. So let's find the roots of this function between, say, -3 numerically and 3. And then, well, we can't just write absolute value of x1 here, but we can define the function anonymously. This is an anonymous function that gets as argument x and returns absolute value of x. And wow, we found the roots of our function, right? So we can use our find roots, and we did this from scratch. This find roots function, we can put anonymous functions for f here, just as we can put real function handles. Okay, back to this. Back to our main story. The main story was we wanted to plot the roots of this wobbly parabola function here. Okay, so for this, let's now plot the positive roots. So what are going to be the positive roots? Let's just copy this line here. Let's copy here, call this positive roots. And we want a plot of positive roots with against zeros. So how many positive roots are there? 5. So I can write here 0, 0, 0, 0, 0, 0. But I won't do that. I'll do something like this. I'll say zeros with the length of positive roots. So it's quite general. Okay, zeros length positive roots, and we want these to be green and maybe with a point size, just like we did earlier at the start of this lesson, of 20. Green dots. Okay. And so what you see in the output here is a zoom in of the output here, where we're actually showing the roots that we found numerically and the roots of the function were found numerically. Okay, so we actually did quite a lot today on something very simple at first, just a parabola, but then we actually found the roots of this parabola numerically. Now this is in a sense the most horrible, I must apologize and say, it's the most horrible from a practical perspective way of finding roots of an equation. Because we're actually searching on a very fine grid, and our accuracy is only as good as a grid. There are much smarter and better ways to do this, and you can either read about such methods or try and think about yourself, about how you would improve on such algorithms, or maybe you've studied them before, but maybe have not implemented them in Julia. And these include the secant method and bisection method and Newton-Raphson method and binary search, and there's many others. Okay, and they would find roots in a much better manner. Still, I think that if you manage to implement such a thing with your students, in front of your students, alongside your students, and actually show them the power of understanding the formalism of mathematics together with something like Julia, then you've really earned your daily wage. So I hope to see you also next week, and next week will be the final session of Math Teachers Code. So this is a 6-week series, and this was now the penultimate one. If you like what you see, one way in which you can show your appreciation is just to register with 1 on Epsilon. And clearly you can also like this video and subscribe to our YouTube channel. You can also follow us on Facebook and Twitter. All the links are down here below. And finally, I'd love it if you try our Epsilon Stream app. It's a completely free app, and it answers anything in the world of K-12 and exploratory mathematics with a collection of curated content that our team has curated for you. So this is Yoni Nazarathi. Bye-bye.